Hello everyone, my name is Ryan Boyd.
And I'm Michael Manoochehri.
And this is the Michael and Ryan Show. Today we're here to talk about best practices for querying massive datasets using Google BigQuery. If you have any questions that come up while you're listening to this or watching this broadcast, feel free to reach out to us on Stack Overflow in the Google-BigQuery tag, or find us on the Google Cloud Platform Developers Plus page, or at our Google Plus profiles and Twitter handles here. We welcome to hear your feedback. All right, so querying massive data sets with Google BigQuery. First of all, let's give you a little bit of history. It used to be when people wanted to query their data sets, they would load their data into a relational database server that looks something like this. That relational database server would get basically all of their data, and it would build indexes on top of that data. And those indexes made it quick to query things that you knew in advance that you wanted to be able to query. So, if you wanted to do some aggregate queries on that data, it might be okay too, based off of those indexes. But if you wanted to do really ad hoc queries to explore your data and understand your data better, you'd often end up doing something called a full table scan. Now, a full table scan is basically reading every single row of your data from disk and processing that each row individually. Now, this is fine if you have a small data set, but as you grow your data and you have, say, hundreds of millions of rows or billions of rows of data, you can only scale your relational database servers so large in a vertical fashion. And Google really, had a challenge. Internally, we had a challenge that we needed to be able to query these types of massive data sets in an interactive style. We needed to get results quickly because those fast results help us iterate on our products, which are necessary for us to build our business. So Google said, well, what if we don't use a typical relational database server? What if we don't rely upon this concept of indexes, but instead embrace the concept of a full table scan? Embrace the idea that we are going to query over every single row of our data. What would we need to make that happen? Well, Google already had tens, hundreds, thousands of servers around the world, and these servers had thousands of disks in them as well. And disk performance is one of the key things that's necessary in order to query massive amounts of data. Now, you can parallelize the queries across all of these machines using typical big data processing techniques, such as the MapReduce algorithm, which Google invented. But the MapReduce algorithm and other big data techniques oftentimes are batch-based. They basically allow you to query your data or process your data in batches. And those batches can sometimes take minutes or hours or even days to get results. Google really needed to have that interactive query speed, so we decided to invent a new technology. And that technology internally is known as Dremel, and externally we've released this to you to use as Google BigQuery, as a service. We built an API and some developer usability features on top of the internal service. So here's what BigQuery looks like. We wanted to give you an idea of what BigQuery looks like, what the architecture is, so you can better understand when you're running your queries what's happening. At the bottom of this diagram is distributed storage. So your data sits on this distributed storage and is read off of the disks by leaf nodes. And each leaf node only reads a small chunk of your data. Each of these leaf nodes would be a CPU or a machine, and they're only responsible for reading that small chunk. And each of them processes their small chunk individually, and as the data flows up the tree through the mixers, the data is aggregated. So if you think about something like a count, the two leaves on the left-hand side would each count the number of records that they're responsible for in the data set that they're responsible for. And then the mixer, as it goes up the tree, would actually sum those two counts. It's a very simple operation. Now, what's important here is that we're reading from the distributed storage only at the bottom of the tree. We're not reading and writing just from the distributed storage throughout the process, as is typically done in a MapReduce-based algorithm. What's also important here is this is a long-lived serving tree. This serving tree exists for all of your queries as a customer, and also exists for the queries of other customers. So it sits around ready to process your queries very quickly. The other thing that I want to point out is we use a thing called columnar storage. Basically, we're storing the data in columns rather than in rows. So as we read the data off of disk, oftentimes you will only need to read very particular columns. You usually when you're running a query, think of like a SQL-like syntax, which is what we use for BigQuery. You're only selecting particular columns and using your where clause on particular columns. So we only need to read those particular columns off of disk. This saves us a lot of our operations, and we'll see how it does that here shortly. All right, so hopefully you understand a little bit about how BigQuery works in the underlying architecture. Now let's dive into some of the types of queries that BigQuery can process. And the first one I want to talk about here is regular expressions. So regular expressions is something that all good geeks know and love and have worked with, back since I started programming on Perl when I first started development, and regular expressions are obviously very well known in Perl. But regular expressions are powerful ways of working with text. Now, the thing with regular expressions, though, is you're changing them often. When you're trying to do these, exploration of your data, you're changing those regular expressions. So you can't build, typical indexes on it like, would work in a relational database. So most relational databases, if you're running regular expressions, you're going to be doing those and doing a full table scan when you write those regular expressions, or if you have to modify them. So this is a very powerful feature that I want to show you. BigQuery supports regular expressions on using matches, replacements, or extractions. It supports all these different types of regular expressions. Let's show you where that power really lies when you're trying to query not just kind of, say, tens of millions or tens of thousands of rows of data, but if you're doing billions of rows of data. So I'm going to start running this query over here, and this is doing an aggregate analysis on 15.7 billion rows of data. So this is 15.7 billion rows, and we're actually going to do a regular expression on every single one of these rows. So we can see a regex match. This data set basically represents something like a log file. In this case, it's a log file of page views on Wikipedia, but imagine in your case it might be a log file of activity on your website, or clicks or views on your ads that you place. And so this log file has titles in it, and those titles represent the page that was viewed. In this case, we want to do a regular expression to find all of those pages that start with a capital G, end with a lowercase e, and have two O's in between. I wonder what that spells out. So we can see that we ran this regular expression. There's 13 tables here. It represents 1 terabyte of underlying data. And we ran this regular expression in 34 seconds. So that was 15.7 billion regular expressions run in 34 seconds across a terabyte of data in the tables. And because of the columnar data store, we actually only had to process about 665 gigabytes of data. But it's still a massive amount of data to find the result that Google, over the year 2010 and the first month of 2011, was the most popular viewed Wikipedia page with, I think that's 1.7 billion, or 1.7 million views, if I'm reading that right. And then we can see some other pages here as well. But the important thing to emphasize here is we're running that 15.7 billion regular expressions in 34 seconds. Imagine trying to do that in your typical relational database server, or even using a MapReduce type algorithm. It would require a lot of processing power and may not even be possible then. All right, so that gives you an idea of the types of regular expressions and the power of BigQuery to run queries on massive data sets. Now I'm going to throw it over to Michael here, and Michael's going to talk about the next section here, which is statistical queries.
Yeah, so statistical queries are another example of the type of query that challenges relational databases when the data sizes are large. And also, if you're using something like a document store or a NoSQL database, or any kind of actual database where you have a distributed system, generally to get statistical aggregate queries, and I'm talking about things like counts, averages, even standard deviations, and things like quantiles. Generally, you'll have to write a MapReduce function of your own. What's great about BigQuery is that you can express these types of queries using SQL or SQL-like language that BigQuery supports. So let's take a look at some examples. We're going to take a look at a public data set we have in BigQuery that you have access to when you sign up, and that's the natality data set. So this is a really interesting data set. It's a record of births in the United States and a collection of data with mother's age, father's age, the baby weight, and other statistics about the births. And I think we have several decades of this data. I think millions and millions of rows of data, actually, obviously. So let's take a look at some queries using some of the statistical functions that BigQuery supports, and to give you a sense of the types of queries you can do. So we're going to come back to our BigQuery UI. Now, this is a query that we were interested in looking at if there's some kind of variance between the baby weights of women who smoke and those who don't during gestation. And so here we're going to run a query to find the average baby weight and the average mother's age. We just picked a random state. We're just going to pick Ohio. And we're going to group by if the mother smokes cigarettes or not. So let's run this query. This is going to give you a sense of the kind of the aggregates over these large data sets. And that was a very quick result. And as you can see, there is a difference in baby weight between the fact that if a mother smoked or not. And the joke I always talk to Ryan about is like, is this a statistical significance? So if you had a statistical package like R, you could actually do some kind of correlation. Here I also ran a standard deviation to give you a sense of that as well. And so this was running over gigabytes of data. And if you were using a relational database, this would take some time. So let's take a look at another statistical query. In this case, we're going to do the count of baby births by gender for large states. And so I've actually picked a number that's, I think, 3 million. So we're going to look at states that have had over 3 million births. I think there's only going to be California and Texas in this example. But here I'm highlighting another interesting function, and that's halving. Halving is like using where in a normal SQL clause, but here we're looking at the aggregate result. So here I'm going to say, give me all of the count of baby births by gender, having a count over 3 million. So let's run that. And here we're going to show like the gender disparity between large states, and this should actually come back pretty quickly as well. So here you can see here's the state of California and the state of Texas, and you can see the count, the difference of birth genders between two states. So again, a ton of data. We're whipping through this really fast, and it's easy to express these types of queries in BigQuery's language. Now here's one. This is one of my favorites. This is, or I'm going to look at a standard deviation, and here we're going to use BigQuery to find outliers in this data set. So I was interested to see how large does a baby have to be several standard deviations above the mean, and I just randomly picked 4. I wanted to see if there are any babies that were 4 standard deviations above the mean. Of course, so you can run that across the entire data set of U.S. births, and very quickly the result comes back, and that's a baby that's about 12 pounds, almost 13 pounds, is a baby that's 4 standard deviations above the mean. That's a pretty chubby baby. So I took this number and I wanted to do a quick ad hoc query to see what months and which states were the chubbiest babies born in. So actually, what's great about BigQuery is you can run these ad hoc aggregate queries. So let's take that number and put it back into another query. And here I'm just going to group by state, year, and month. And I'm going to see which state for which date were the fattest babies born, or let's say the most giant babies. And so shockingly, Maryland in December 1990, had quite a lot of very chubby babies. I went to Google to see what was going on. I couldn't find a definitive answer. So if anyone has any idea why Maryland in December 1990 had such chubby babies, please let me know. But these are the kind of queries you can do that are very difficult on other systems and are pretty easy and quick with BigQuery. So let's take a look at some other functions that BigQuery is really good at. Earlier, Ryan talked about some of the log data. We were looking at Wikipedia page view data. BigQuery is excellent for log data. I mean, it's one of the kind of canonical use cases for it. So it has certain specific functions that help you format and parse timestamps and URLs and IPs. So you can do things like take a UTC formatted timestamp and format it into a more human readable string. We have functions to parse URLs. So if you're looking at domains, grouping things by domains, that's really easy. And you can parse and format IP addresses and convert them from integers back into a string format and things like that. So let's do a few quick examples just to show you what I'm talking about. Let's go back to our BigQuery web UI. And we're going to take a look at a quick domain query. So this is a really interesting public data set we have as well. One of our colleagues, Ilya, who's on the Chrome team, he was really interested in GitHub public data. So he loaded up a bunch of the data from the GitHub public timeline, which is great stuff like repository homepage, commit message, really cool stuff. And we have some examples on our website in our documentation about ways you can query this and do some interesting, what I call the poor man's sentiment analysis by studying commit string messages and things like that. You can find the most popular projects. So in this case, what we're doing is we're just going to look at the project homepage domains with the most activity. So in GitHub, you can say, this is my homepage for my project, and oftentimes it is GitHub. So let's just take a quick look at this. I'm using the domain. I'm using the domain function, and I'm grouping by domain. So here you can see people have with the domain github.com, which is the most common, google.com, that might even be code.google.com, Khan Academy, Mozilla. So you can do these kind of analysis on your logs to find out, for example, refers, like what is the most common refer, etc. So really useful stuff when it comes to logs and IP. Oh, and let's do a quick timestamp query as well. We're going to take a quick look at this one. This is an interesting one. Going back to our Wikipedia data set, I was interested in knowing what moment in time are the most, the most edited pages are. So here's an example. I just randomly chose Obama. I wanted to see what moment to the second were the most edits made to pages containing the name Obama. So you can actually do these kind of queries with BigQuery. This is going to look through gigabytes and gigabytes of data, and I found out that on 7/29/2008 at a particular time there were 5 revisions being made, and it's really interesting to see this kind of stuff happen. You can see you can bucket by time when revisions are being made and find really interesting visualizations and interesting graphs using this type of data. So really interesting stuff there. This is one of the most common questions we get, are geospatial queries. Ever since we both started the project, almost every time we meet developers, they ask us about this. So we made a special effort to talk a little bit about geospatial queries in our query cookbook documentation. So this is a really interesting one, and I think Ryan has been playing a lot with geospatial queries with your car data. We did some automotive data analysis, and we can talk about that on another GDL. It's on our videos page where we talk about sensor data. So let's do a few examples of geospatial queries. So BigQuery has a lot of mathematical functions besides the statistical aggregate mathematical functions. Cosine, sine, trigonometric functions, rounding functions, all kinds of things. So you can actually use these functions to do things like approximate a bounding circle using some of the trig functions. And of course, you can do a range for the bounding box as well. So let's take a look at some of those examples. We have some here. Let's take a quick look. So let's look at a geospatial bounding box. This is a pretty simple one. We're going to take a latitude and longitude, and we're going to find a range in between the boundaries of this latitude and longitude grouping. And here we're going to look at San Francisco. We both live in San Francisco, and we're going to look at the average temperature from weather station data. We have an interesting data set in BigQuery. It's the general surface summary data. So every day, all the weather stations that are public, collect data, and this is a data set of all of that data that we have available since, I think it's like 1929 or 1930. So millions and millions of records, really interesting stuff. What we did was we took this data and we attached a latitude and longitude to each station. And here we're able to actually run these geospatial queries and get aggregate results for any station that falls within a certain geographic range. It's really interesting. So here we're going to run a query around San Francisco, and we're going to find we're going to group by year and month, and we're going to produce a listing of the average temperature and also the minimum and maximum over a range. And here, that was a very quick query, just a few seconds over gigabytes of data. And this is another kind of query that would be great for a visualization. You can actually bucket by year or month, produce the average, the minimum, the max. Very interesting for that specific range. So really, really good query there. Now let's do a bounding circle. Now, Ryan, we spent a lot of time trying to learn about the bounding circle. Can you tell us a little bit about how this bounding circle query works?
Yeah, I mean, basically the bounding circle query is just kind of using basic trig functions, and assuming that the world is perfectly spherical. The world isn't perfectly spherical, so you won't get totally accurate results if you're near the poles. But oftentimes, this type of bounding box query or bounding circle query is actually adequate for most places in the world. So it's a pretty interesting query to run. You can see all the trig functions that we're using. And why don't we kick off that query here? And we're finding the average temperature for all the weather stations that are around Denver, Colorado in this particular query.
We picked Denver, Colorado, and this is actually for the month of January. We picked Denver because there's a wide variation of weather between winter and summer. So as you can see here, this will produce the distance away from this middle of the circle, along with the latitude and longitude of the weather station and the temperature as well, which is really interesting. So you can see the temperatures here are pretty cold. To just give you an example of the cool things you can do, you can switch this up to June or July. Let's take July.
So we were about like 30 degrees or so, I believe, Fahrenheit. So let's switching to July. What do we end up with here?
Should be warmer. Okay,
70-ish.
Sounds pretty good. Very mild, very great. love to be in Denver then. Looks good. So this exact example is on our query cookbook on the Google developers page for BigQuery, and I hope you check it out if you're interested in this type of query. All right, so let's talk about nested and repeated data. So BigQuery, to get your data into BigQuery, you have to ingest source files, and your source files can be in CSV data, which is rectangular. Log-shaped data fits into this very well. But you can also ingest JSON data, and your JSON data can model a nested and repeated data set. So let me just show you a little bit what I mean. Here's an example I like to use. I call it the social music store data set. So in this case, imagine a social music store where you have a lot of customers and they can either listen to or purchase music. And your logs will record each of these events, right? So here's an example of Michael is listening to a song and he decides to purchase a song. The two types of data, listening and purchasing, have different data types in that when you listen, it doesn't cost anything, so you're not recording a cost. And when you purchase something, you're actually buying it, so there's a cost associated with that. And so you could model this in a flat CSV style format, but as you can see, there's redundancy, there's some null values. You may have to have a separate field for listen and purchase, like a flag that describes it. So this works, there's nothing wrong with it, and BigQuery can actually handle this type of data if this is how you have it. But imagine another way, maybe a different way to model this data to give you some added advantages, and I'll talk about that in a second. So you can actually take that rectangular data and model it like this in a nested and repeated way. So every day I can actually have a top level record called Michael, and it could show my activities. So in this case I've highlighted the listens, and that is a separate model, a separate type of record. And then below it is purchases. So as you can see, there's a cost associated with it. Basically I can have two different types of records within this Michael record. So what does this mean? So why is there an advantage here? Well, there's actually several.
I just want to say, I mean, it's actually kind of a much more natural way to model the data rather than flattening it out. And it's also a way that's used by a lot of standard NoSQL databases and other databases to model data. So that makes BigQuery really compatible if you're trying to analyze your massive data set that's stored in a typical NoSQL database. You can load it into BigQuery and run the aggregate queries there.
Yeah, no doubt. Like as I was saying before, this is a big advantage. And if you're using something like Mongo, you can actually export the data as JSON. It's the native file format for some of those document stores. So really easy to get the data into BigQuery that way. But actually, this kind of structure, this nested and repeated structure, supports some additional query functionality, which is really useful. One is within record. So in this case, what you can do is actually find aggregate data within a specific record, and I'll explain how that works in a second. The other is position. If you ingest your data in a nested way with repeated values, BigQuery actually remembers the position of each one. So you can do cool things like playlists and show the position of a song in a playlist. And I'll give you an example in a second. Just to give you an idea, this is the kind of query, how many users have listened to a particular artist, for example, right? This kind of query you can actually you can say, well, the count of people that had listened to this particular artist in this playlist, you can have a full count, an aggregate over the entire data set. Or you can actually use within record to actually pull out the average for each individual user, which is super useful. And here's an example of what position is a particular artist song in a daily user playlist. Here I'm using the position function to actually pull that out. I have some sample data. I have a fake music store, and we can actually look at some of these queries in action. So let's see. Let's start with the within record query. So here I'm going to look for, in my fake music store, I'm going to see, I'm going to run a subquery to find users who are listening to the artist Psy, and I'm going to find the count within record of Psy songs. So let's see. It's a pretty small data set, but in this case, you can see like I have apparently 2 Psy songs in my playlist. I didn't know there was another popular Psy song, but it's in there. And now let's take a look at position. So this is very interesting. I'm going to look at the actual position of a song in a playlist. As you saw, I may have multiple songs by a particular artist in my playlist. Now here I can say find the actual position. So you can see in this case, each of the users in our data set has the song in a different position. This is very useful for example, if you want to know things like bouncing, like when people come to your site, when do they bounce out? You can use playlist data or shopping data. What kind of things are people buying in sequence? There's a lot of applications for this type of query, and it's actually supported by BigQuery using nested or repeated data. So yeah, so I think that pretty much wraps up our querying session. A lot of the queries you saw today are available in our query cookbook, which is on developers.google.com/BigQuery. And of course, we want to hear from you. We want to know what kind of things you're doing and what kind of queries you're running, what you'd like to see. If there's a query you're having trouble with, of course, Stack Overflow is a good place for that. Post your question using the Google-BigQuery tag. And some of our engineers are on that site all the time, and we'll get back to you as soon as we can.
Well, I think that about wraps it up. I'm Ryan.
Yeah, I'm Michael.
And this is the Michael and Ryan Show. Thank you.